This question is one which I decided to make extra credit, but I will show you how to go about solving it. We have a loop-de-loop, and we have a block which is sliding down. So photo 1 is taken when the block is at its starting point, and photo 2 is taken when it is at this location in the loop-de-loop, so exactly halfway up. Now, we were told that the loop-de-loop has some radius r. We weren't told what it was. And we were told that the object initially starts at 4r. And originally we were being asked to find what is the velocity of the block at photo 2, and also what is the force on the block at photo 2. So, since we're talking about forces, I'm going to draw a free body diagram corresponding to photo 2. The block would feel the weight force down, and the normal force, the force from the track, would point inwards towards the center of the block, or sorry, the center of the loop. So what that means is that the direction of the normal force, because it's pointed towards the center of the loop, the normal force is going to be our centripetal force. So that's a piece of information we will use a little bit later on. Now, to find out what the velocity of the block is, we can use conservation of energy. Kinetic energy in photo 1 plus potential energy in photo 1 plus work in minus work out equals kinetic energy in photo 2 plus potential energy in photo 2. So, kinetic energy in photo 1, it's not moving, there's no kinetic energy. But it is at an elevated position, so it does have potential energy. There's no jetpack strapped to it, so there's no work in. There's no friction, so there's no work out. Kinetic energy, it does have kinetic energy in photo 2, and it also has potential energy in photo 2. So all of this now simplifies down to potential energy in photo 1 equals Ke2 plus Pe2, the kinetic energy over here plus the potential energy over here. So let's expand this out. Pe1 is mgh1 is equal to Ke2 half mv2 squared plus Pe2, which is mgh2. The mass is unknown. I said you could allow it to be 1 kilogram, but there is one other thing that we could do. Notice that every term here has mass, which means that mass is multiplied into every term. We can simplify this whole thing by dividing the mass out. We can, whenever you have something that's multiplied across all terms, you can divide it out, which means you just need to cancel the mass in all of the terms. So the mass was never really relevant. If you don't like doing this, just use a mass of 1 and you'll end up in the same place. In fact, why don't we do that? So the mass is 1, g is 9.81, height 1 is 4r, is equal to 1/2 times mass 1, velocity 2 is unknown, plus mass 1, g 9.81, times the height over here is r. Okay, now let us simplify everything that we have here. 9.81 times 4, that's going to give us, I think I'll use my calculator for this, 39.24. The r is multiplied in, so we have to keep it as a term over here. But this is equal to half times 1 times v2 squared plus 1 times 9.81 times r. Okay, 39.24 minus 9.81 gives us 29.43. So we can move this r term and subtract it from this other r term over here. So that's going to give us 29.43 r equals 1/2 v2 squared. Multiply both sides by 2, 58.86. That will clear the 1/2 over here. So that gives us v2 squared equals 58.86 times r, and v2 is going to be the square root of that. So we could write that as the square root of 58.86 r. That would be the simplest way to write it. Notice that over here we have written an expression for v2, but we never knew what the radius was. And as such, we have to write v2 in terms of the radius. There's no way to avoid that. The v2 is going to change depending on this, whether this was a 1 meter loop or a 2 meter loop or a 10 meter loop or whatever. So we need to write v2 in terms of r. So the mass was irrelevant, but the radius is relevant. So this is as far as we can go, a v2 which is in terms of r. Now, we were also asked how big is the force of the track on the block. That's basically asking how big is the normal force. Now, we know that the normal force happens to be equal to the centripetal force, because the normal force is what is pushing the block inwards towards the center at this point in the track. So, centripetal force is equal to mass times centripetal acceleration. And centripetal acceleration is equal to the tangential velocity squared divided by the radius, which is equal to 58.86 r. Take the square root, that gets squared. So radical 58.86 r squared, that is the thing that has to get squared, divided by the radius, which is r. So that's going to give us 58.86 r divided by r. The r's cancel out, and we get an acceleration of 58.86 meters per second squared. So this is the acceleration on the block. And interestingly enough, the acceleration does not depend on what the radius is. The velocity depended on the radius, but in the calculation for acceleration, the radius cancels out and you get the same acceleration in all cases. Since this is the centripetal acceleration, we just need to multiply this by the mass to find the normal force. So the normal force is equal to the centripetal force is equal to mass times centripetal acceleration, which is, the mass is unknown, but the acceleration was 58.86, so we just need to say it would be 58.86 mass multiplied by, or sorry, the units would be newtons. So this would be the size of the centripetal force, 58.86 times the mass of the object. Like I said, I have made this an extra credit question. It can be a little bit confusing, perhaps, if you have so many unknowns in this question, which is one of the reasons why I felt it was a little unfair to keep it as a standard question. But the logic for solving it is precisely the same as what we have seen in many questions so far. We used conservation of energy to figure out what the velocity was, and we used centripetal force to figure out the centripetal acceleration, and finally, what the normal force was. In this question, we have an object which is on a compressed spring in photo 1. And in photo 2, the spring is uncompressed, the object is launched upwards, and in photo 2, it reaches its peak. Now, the information we've been given is the spring constant of the spring was 12 newtons per centimeter, which is equal to 1200 newtons per meter. We do everything in meters over here, so if it's 12 per centimeter, it must be 1200 per meter. We were also told that the vertical distance between the object in photo 2 and the expanded length of the spring was 5 meters. And this distance over here, from the compressed spring to the expanded spring, is unknown. That's what we're solving for. I believe we called this D in the question. So given all of this information, we need to solve for what D is. The last thing we were told was that the mass of this object was 15 grams, which is 0.015 kilograms. So a couple of conversions that you have to do before you can start working with conservation of energy. It's a nuisance, isn't it? Anyway, conservation of energy tells us that the kinetic energy in photo 1 plus the potential energy in photo 1 plus any work that came in minus any work that went out is equal to the kinetic energy in photo 2 plus the potential energy in photo 2. In photo 1, our object is not moving. There's no kinetic energy. But it is on top of a coiled spring, so there is potential energy due to the spring. Work in. This object is not on a jetpack, so there's no work in. Work out. This object is not experiencing any friction, so there's no work out. Equals kinetic energy 2. At the peak of motion, this object is not moving. Plus potential energy 2. This now has potential energy due to gravity. It does not have any spring potential energy, however. So that gives us 1/2 k delta x1 squared. That is the spring potential energy. Oh, by the way, I forgot to say something. I'm going to set this point over here, this level, as being the lowest point for the spring, because or the lowest point for potential energy, my origin from which I'm measuring my gravitational potential energy, because that way I don't have to worry about gravitational potential energy in both sides. On the left side it'll be 0, and on the right side it's going to be 5 due to the height of 5 plus d. So over here on the left side, on photo 1, we have only spring potential energy because the object is at the origin. And that's going to be equal to mgh, which is the gravitational potential energy on the right side because this spring is now at its natural length. Let's plug in everything we know. 1/2 times k, 1200, times delta x. This thing was compressed by a distance of d, so that now becomes d squared is equal to mass 0.015 times gravity 9.81 times the height. The height has now become 5 plus d. That is how far it has ascended over its original position, which is what we consider to be the origin. So now let's simplify all of this. 600d squared is equal to, let's multiply this out. 0.015 times 9.81 gives us 0.14715. So that first has to get multiplied by 5 because this is basically a FOIL we're doing. So let's actually write this out step by step. Okay. So 0.14715 multiplied by 5 gives us 0.73575. So this right side now becomes 0.73575 plus 0.14715 d. Rewrite this a little bit, and we get 600 d squared minus 0.14715 d minus 0.73575 is all equal to 0. This is a quadratic equation, and we can solve the quadratic equation using the quadratic formula. I'm not going to write out the whole thing. I happen to have a program on my calculator that solves quadratic formula for me. If you don't have such a program, you could either use the quadratic formula, do it out longhand, or you could plug this into the y equals of your calculator and write it in as a function over here, and then find out where it crosses the x-axis. Either way would be a perfectly fine thing to do. So now let's run the quadratic formula. A is 600, B is negative 0.14715, and C is negative 0.73575. So we get two different answers. One of them is a negative number, but that would correspond to an expansion rather than a contraction of this. So it's really only the top number, 0.035, which can possibly be correct. So the compression of the spring was 0.035 meters, and that led to the object being shot upwards by 5 meters over the natural length of the spring. In this question, we have an object which is sliding down a ramp. The ramp has some friction on it. It reaches a flat plane that has no friction, and it's going to compress a stopper that has a spring attached to it. So photo 1 corresponds to when this object is at its maximum height. Because I have limited room over here, I'm going to draw some of these other photos in shorthand. Photo 2 is where it reaches the bottom of the ramp. Photo 3 is where it compresses the spring. Photo 4 is where it returns to the bottom of the ramp and the spring uncompresses. And photo 5 is where it travels midway up the ramp. And that makes sense because this ramp has friction, and the block has lost some of its energy to that friction. So it doesn't go up quite as high as it did. It doesn't regain the potential energy that it once had at photo 1. So this is photo 1. This is photo 2. This is photo 3. So photo 2 corresponds to when the object is at the base of the ramp. Photo 3 is when it has completely compressed the spring. Photo 4 is when it returns to the base of the ramp. And photo 5 is when it has gotten partway back up the ramp. Now, let's look at all of the information that we have been told. The initial height of the block is 2 meters. This angle here is 30 degrees. The mass of the block is 10 kilograms. The compression of this spring is 500 newtons per meter. Or sorry, that's the spring constant. The compression of the spring is 0.75 meters. And at the end of this story, this object is going to travel up to some distance h, and it will have traveled some displacement, delta x, over here. Now, one last thing which is going to be important a little bit later on is we need to find out what is the length of this ramp. We will need that towards the end of this question. Fortunately, it's easy to find because the height divided by this displacement is going to be equal to the sine of 30 degrees. Because this height, this is the opposite side of this angle, and this is the hypotenuse. A little bit of rearrangement, and we get that delta x would be equal to 2 divided by sine of 30 degrees, which is equal to 4. So the length of this ramp is 4 meters. Now that we have all of that stated, let's go ahead and solve what this question was actually asking for. Now, this question told us that we have the object initially stationary over here, but it's moving at photo 2, and then it compresses the spring at photo 3. We can easily find the potential energy at photo 1, but then we're stuck. Why? Because we don't know the coefficient of friction of this ramp. We were never told the coefficient of friction of this ramp, so we can never find out how much friction there is, at least if we're trying to solve it directly. So we're going to have to find another way of getting the velocity at this point, which was what the first part of this question was asking for, the velocity here. Fortunately, we were told a lot of information about photo 3. We were told the spring constant and the compression. We can use that to get the velocity. So that's precisely what we're going to do. Now, I'm not going to write out the full conservation of energy equation over and over again because I simply don't have the space for it. So I'm going to write this out in shorthand. In photo 2, this object has kinetic energy. It is clearly moving. But it has no potential energy because now it has reached the lowest point of this entire situation over here. So there's kinetic energy, there's no potential energy. Between photo 2 and photo 3, there's no work in because this object wasn't wearing a jetpack. And because there's no friction on this ground over here, there's no work out either. So that means that the only thing which doesn't get cancelled out between photo 2 and photo 3, at least on the left side, is the kinetic energy in photo 2. What about in photo 3? Well, over here, this object has compressed the spring. So there is spring potential energy, but now it has stopped moving, so there's no kinetic energy left over. So that means that for part A, which is between photo 2 and photo 3, kinetic energy in 2 equals potential energy in 3. Cool. Let's start expanding this out. Kinetic energy in 2 is 1/2 mass times velocity in photo 2 squared. And that's going to be equal to 1/2 times k times delta x, the compression of the spring, squared. Substitute in everything we know. 1/2 times the mass, we were told, is 10. The velocity is the unknown, is equal to 1/2 times k, 500, times the compression, 0.75, squared. Now let's start simplifying. Half of 10 is 5. 5v2 squared is equal to half of 500 times 0.75 squared. That works out to 140.625. So that's the potential energy at point 3. 140.625 joules. Next, divide both sides by 5. That gives us 28.125. And finally, take the square root. That gives us 5.3. So the velocity in photo 2 has a size of 5.3 meters per second. So this is the first thing that we've been able to solve for. Part B was asking about how much work gets lost between photo 1 and photo 2. So, in photo 1, this object is not moving, so it has no kinetic energy, but it is at an elevation, so it does have potential energy. It's on a rough surface. It's not wearing a jetpack, so there's no work in, but it's on a rough surface, so there is work out. And all of that is equal to the kinetic energy in photo 2. There is no potential energy here because now we have reached the bottom and the spring has not yet been compressed. Now let's substitute in everything that we know, or at least let's expand this out. PE1 is due to height, so that's going to be mgh minus the work out equals 1/2 mv2 squared. So substitute everything we know. Mass 10, gravity 9.81, height 2 meters minus work out is equal to 1/2 times mass 10 times the velocity, which is 5.3, we already worked that out, squared. So 10 times 9.81 times 2, that gives us 196.2 minus work out equals 1/2 times 10 times 5.3 squared. 1/2 times 10 times 5.3 squared, that gives us 140 well, it should really be 140.625 because the kinetic energy at 2 equals the potential energy at 3. We already figured out that potential energy at 3 was 140.625, so that's what this number is over here. So 196.2 minus 140.625 equals 55.575. So work out is equal to 196.2 minus 140.625, which is 55.575 joules. Cool. We have now solved for the work out between photo 1 and photo 2, the amount of work that friction did on this surface. Let's keep going. Photo 3 to photo 4 was the subject of part C. In photo 3, there is no kinetic energy, the object is not moving, but the spring is compressed, so you do have potential energy. The object still isn't wearing a jetpack, so there's no work in, and there was no friction on the surface, so there's no work out. In photo 4, this object is moving when it gets back to the base of this ramp, so there is kinetic energy. But because it's still on level ground, and because this spring has elongated, there is no more potential energy. So there's only kinetic energy at this point. So let's expand this out. 1/2 times k times delta x3 squared is equal to KE3 is 1/2 times mass times the velocity at 4 squared. Now let's substitute in everything we know. 1/2 times K is 500 times its original compression in photo 3 was 0.75 squared is equal to 1/2 times mass 10 times velocity at photo 4, which is the unknown, squared. Let's simplify all of this. Half times 500 times 0.75 squared will work out to half times 500 times 0.75 squared is 140.625. That's interesting. Didn't we see this number before? Yeah, we had already calculated this. So now we have 140.625 equals half of 10 times v4 squared, which is 5 v4 squared. Now that's interesting. The situation between photo 2 and photo 3 looks like a mirror image of the situation between photo 3 and photo 4. Huh. That should come as no surprise, because the kinetic energy over here went entirely into the potential energy in photo 3. There was no energy gain and there was no energy lost. It was simply a transfer of the form of energy. It transformed from kinetic energy into potential energy in photo 3, and again from potential energy back into kinetic energy in photo 4. Again, there's no friction anywhere between these three photos, so there was no gain, there was no loss, and the kinetic energy at photo 4 must be equal to the potential energy at photo 3, which is in turn equal to the kinetic energy at photo 2. So I can even skip that second last step, and I can confidently say that the velocity at photo 4 must be 5.3 meters per second, exactly the same velocity as what was there at photo 2, because the kinetic energies are the same in both of these locations. Now, this is starting to get a little bit congested, so I'm going to draw some divider lines over here. Okay, the last step then is part D. In part D, we needed to solve for what is the height, the final height that this reaches. Now, before we can do that, I want to specify that the height over here divided by the delta x, the distance that it travels up the ramp in between photo 4 and photo 5, must be equal to the sine of this angle, because h is the opposite side. So h divided by delta x is opposite over hypotenuse, must be the sine of this angle, which is still 30 degrees. That piece of information is going to come in handy a little bit later down the line. Now, for part D, between photo 4 and photo 5, at photo 4 there is kinetic energy, so there's KE4. There is no potential energy at photo 4. Work in, thing still isn't wearing a jetpack. Work out, there is going to be work out because you're moving up a rough surface. So minus the work out is all equal to, at this point over here, there is no potential, there's no kinetic energy because this thing is not moving, but there is potential energy. Okay, let's expand out what we have here. So KE4, that would be 1/2 mass times the velocity at 4 squared, minus work out. We don't know what the work out is over here. Let's expand this out nevertheless. So that's force of kinetic friction times delta x times the cosine of the angle between them is all equal to the potential energy at point 5, which is given by mgh. Now let's substitute in for what we know. The things that we know are 1/2 times the mass is 10. The velocity at point 4 we already solved for is 5.3 squared, minus, now we run into a problem. We don't know what the force of kinetic friction is, and without that, we can't solve for either the displacement or the height, because then we have too many unknowns in this equation. So what do we do? Well, we can go back to part B over here. We've already figured out what the work out is over here. And we also figured out that the displacement of the object across the first photo, between photo 1 and photo 2, was 4 meters. That was the displacement here. So what can we say? We can say that the force of kinetic friction multiplied by the displacement multiplied by the cos of the angle between them is equal to the work out. So, the force of kinetic friction is our unknown, times the displacement, 4, times cosine of phi. This object was moving down the ramp, so its displacement was down the ramp, but the friction was pointed up the ramp. So that means that these two were 180 degrees apart. It's the cos of 180. And all of that's equal to work out, which we previously calculated was 55.575. Now, cosine of 180 happens to be -1. And since this is multiplied by 4, all I need to do is, this whole thing will simplify down to the force of kinetic friction times 4 equals 55.575. So, that leaves us with 55.575 divided by 4, which is 13.89. That is the size of the kinetic friction. So now we can use the same kinetic friction over here because the value of the kinetic friction does not change. Only the work that it's doing alters between photo 1 to photo 2 versus photo 4 to photo 5. So 13.89 multiplied by whatever this displacement is, that would be delta x. But if I rearrange this, I could say that delta x is equal to h over sine 30. So let me write it like that. Or maybe I can even do that in a later step. All of this is equal to m, the mass, 10, times g, which is 9.81, times the height, which is as yet unknown. Let's keep simplifying this. Half times 10 times 5.3 squared. We've done this calculation before. It works out to 140.625. Minus, the delta x is not known, but if h over delta x gives me sine of 30, then I can rewrite this term over here as h over sine 30, because h over sine 30 must be equal to delta x. The angle between them is 180 degrees again, because this is traveling up the ramp, friction points down the ramp, and the cos of 180 degrees is -1, but that gets cancelled by the absolute value sign that we have here. So we could write it like that if we wanted to be particularly rigorous about it. 9.81 times 10 gives us 98.1 h. And now this whole thing can be simplified still further. 140.625 minus 13.89 divided by the sine of 30 degrees. 27.79, let's call it. Equals 98.1 times the height. So, add 27.7h to both sides. That's 125.8. So now we have 140.625 is equal to 125.89 h. And so the last thing is to solve for h, which is 140.625 divided by 125.8, which is 1.12 meters. So now we are at last at the end of this puzzle. The box travels 1.12 meters up the ramp. That is its final height above the ground when it finally comes to a stop.